This is the lecture for Friday, April 3rd, and in this video we are going to discuss galvanic or voltaic cells, or how is it we use redox reactions that we worked on balancing at the beginning of the week to get useful work. So the questions we're going to address starting today are: what exactly is a voltaic cell or a galvanic cell, and how does it work? How is the cell potential connected to free energy changes? How do we connect spontaneity, non-spontaneity to doing useful work in electrochemistry? And how do we tell people or denote what is in the cell? Let's start by considering the oxidation of zinc by copper 2+ ions. So in this reaction, our zinc is being oxidized. So then it must be the reducer or the reducing agent. And if we went in the reverse reaction, zinc would be reduced and copper would be oxidized, so zinc would be the oxidizing agent. So written in the forward direction, the zinc is being oxidized by the copper +2 ion. So the copper +2 ion is the oxidizing agent or the oxidizer. So there's always this coupling that goes on during redox reactions, right? So we want to think about those terms as we go forward. So as we mentioned, we can split this up into the two half reactions: oxidation of zinc into zinc 2 ions and 2 electrons, and the reduction of copper by adding negative electrons to copper metal. So that is our oxidation reaction. So if we looked up all the values on our table and did products minus reactants to find what is the free energy change for this reaction, we would find that it is a negative delta G. So we know it's a spontaneous reaction, that if we put zinc metal into contact with solution that has copper 2+ ions, this reaction is going to happen. So let's look at a picture of that and think about if we could watch what was going on the molecular level, what would be happening, right? So here's our picture of our zinc metal in some copper sulfate solution. So it's blue from the copper ions. So what's going to happen is the electrons are given from the zinc to the copper ions, and then the copper becomes copper metal, and the zinc metal becomes zinc ions. So that's what's going on, and that will happen right on the surface of this metal, piece of metal inside of our beaker. And if I could show you this, I would show you this, but I'm sure you could Google it and find a video online if you wanted to of this reaction, or just watch a video, which I'll talk about in a moment. So this is what's going to happen, and it's going to happen spontaneously, right? Because the delta G, the change in free energy, is negative. But what if we could separate these two processes? If we separate these two processes into the two separate half reactions, we could use those electrons flowing from zinc to copper. And that's what we call an electrochemical cell, a voltaic cell or a galvanic cell. So if we separate things out so that the oxidation happens at what's called the anode, and the reduction happens at what's called the cathode, we can get the flow of electrons outside of this process. So if I just put the piece of metal in the solution, it's just going to happen in the solution, and I can't get any useful work out of it. But if I separate things, I can get useful work out of it. So what you might want to do at this point is either pause the video and find this, click on this link. It will be in the PowerPoint slides that will be on Sakai, and watch this zinc copper cell animation from the textbook, or you can just wait. There's another link at the end of this video. You can watch all of those videos at that time. So if we can separate things, so this link is really cool animation where it actually shows the flow of electrons. This picture is just a stopped picture of the same thing, right? So if we could separate the oxidation to the anode side and the reduction to the cathode side, we could get a flow of electrons and use those electrons to do work, right? because the flow of electrons is electricity. So that's how we can make work happen. So a voltaic cell or electrochemical cell separates these two things into half reactions. So we see that the oxidation reaction is happening at the anode. So always remember that, oxidation at the anode. And I've always thought that that would be a great name for like an indie rock band, oxidation at the anode. But maybe that's just me. So anyway, we can separate oxidation and reduction into two separate things, right? For this to work, we still have to have things connected so the electrons can flow. So we have a wire that goes through a voltmeter that connects my anode to my cathode electrode, right? So the metal pieces are called electrodes. I also have to have a connection between the two solutions so that ions can move, because we can imagine that if this oxidation at the anode is happening, we're going to get a lot of buildup of zinc plus 2 ions, because this solution didn't have any zinc ions. And then as this reaction progresses, the zinc comes off as zinc plus 2 ions. We get a buildup of positive charge. So if we have a salt bridge here that connects things, the negative ions in the salt bridge can flow to maintain a charge balance. And that also completes our circuit. So we have electrons flowing, charge flowing like this, which you'll see really well if you watch the link with the animation. So in this case, in our copper-zinc reaction, the metals, the electrodes, are involved in the reaction. They don't have to always be involved in the reaction. We could have an inert metal there, say a platinum electrode, or a graphite rod would be another inert electrode that is typically used. So not all oxidation reduction reactions have to involve the metal that's being used. We can imagine situations where the metal is not being used in the reaction, used up in the reaction. So this reaction is going to just keep going and going and going until we run out of stuff, right? Until we run out of copper. So we think about how delta G is changing over the course of a reaction. So we mentioned this in the last unit, but we haven't really dug into that idea. So we will during this unit. So delta G naught, the standard free energy change, is just the difference between the free energy, the standard free energy of reactants and products. But the free energy change not standard is what happens as the reaction is in progress. Right? And that changes as the concentrations of reactants and products change. So we have that slowly changing, and eventually delta G becomes equal to 0, right? We reach equilibrium and the reaction just stops. So when that happens, we're not going to have electron flow happening in our voltaic cell anymore. So let's think a little bit more about how it is the free energy change is connected to this potential that we're looking at or we're measuring, right? We're measuring the voltage potential between those two electrodes. So the whole purpose of having a voltaic cell is to convert this free energy change of a spontaneous reaction into electrical energy. That is our point, right? We want to convert the spontaneous energy of the chemical reaction into kinetic energy of electrons moving. And that's electricity. And we can use that to do work. Right? So reactions with a lot of pushing or pulling power generate a really high potential difference or a high voltage. And those with a small potential difference will have a smaller voltage. So the Systems International unit of electrical potential is called the volt. A volt is defined so that a charge of 1 coulomb falling through a potential difference of 1 volt is equal to 1 joule. So 1 volt times coulomb equals a joule. Volt, coulomb, joule. Or we could think of that as 1 volt equals 1 joule per coulomb. So our cell potential, which we're going to use the letter E to represent cell potential, is what is the difference in voltage between our two electrodes, or EMF. And that is connected to the Gibbs free energy change in the following equation, right? So our delta G is equal to the negative NFE, where N is the number of moles of electrons being transferred in our redox reaction. F is Faraday's constant, which is 9.6485 times 10 to the fourth coulombs per mole, and our potential is measured in volts. So we see that if we have all of these together, moles would cancel. Coulombs times volt is equal to a joule. So we get a free energy change in joules. So note here that if we have a positive potential, we will get a negative free energy change. So that would be a spontaneous reaction. So a positive, let's put that there, E will give us a negative delta G. Kind of looks like a G there. So eventually, as I mentioned before, if delta G is equal to 0, we've reached equilibrium, so we're not going to get electrons to flow. So that's what is happening when we have a dead battery or an exhausted battery, is a cell that has already reached its equilibrium potential difference, which is equal to 0, which gets us a delta G equal to 0, and no electrons are flowing. We can also define a standard cell potential. So we can think of our standard free energy change as equal to negative NFE cell, where this is the cell potential in its standard state. So this would mean all the species are taking part in this reaction are in their standard states. So mostly that means metals are solid metals, and anything that is in solution would have to be a 1 molar concentration of solution. Note that our standard cell potential does not change regardless of how we write the equation. Let me show you an example. So here's our zinc-copper reaction. So as I mentioned, it is spontaneous. It is a negative 212 kilojoule reaction. So that is negative, so delta G is negative, so it's spontaneous, and our E cell is positive, so it's spontaneous. So if we multiply that by 2, we would multiply delta G by 2, right? If we multiply the whole reaction by 2, then we would have twice as much free energy change, so negative 424 kilojoules for this reaction. But notice that the E cell is the same. So if we look at this equation, but if we double everything that's going on here, we've also doubled the number of electrons that are being transferred, right? So in the first reaction, it's 2 electrons, and in the second, it's 4. So if we divide this by 2 or this by 4, we're still going to get a 1.10 volt cell potential. Okay. So here would be maybe a good place to pause, write down any questions you have, and bring those questions to one of the opportunities for questions Google Meet sessions that are happening every week. So far when we're looking at all of our cells, we always have this whole picture, right? We've got the whole picture where we can see what's in solution, we can see what the anode is, we can see what the cathode is, which metal, we can see that there is a salt bridge that is making an ion connection between the two, and we have a voltmeter. So just looking at this picture, we see I've got a positive reading on the voltmeter, so this must be a spontaneous reaction because I've got a positive cell potential. And so oxidation is happening at the anode. So my copper is being oxidized. My silver ions are being reduced to copper. So I can see what's going on, but I have to have this whole picture. And I know what the concentrations are. So it looks like this is probably the standard cell potential since all my concentrations are 1 molar. So we want to think about how do we tell people what's in the cell without drawing the whole picture of the cell. Well, one of the things we can do is write the reactions. What are the half reactions taking place and what's the overall reaction taking place? So at the anode, oxidation at the anode, my cheesy joke about a band, oxidation at the anode, so my copper is being oxidized to copper 2 plus and 2 electrons. Reduction at the cathode, so my silver ions are being reduced to silver metal. So if I want to add this up, I do need to multiply this whole thing, right, by 2, because if I'm producing 2 electrons in the oxidation step, I need to use up both of those electrons, 2 electrons in the reduction step. So overall, we've got copper plus 2 silver ions going to silver metal plus copper 2 plus ions. So one way we can denote what's in the cell is to say this is the reaction that's happening in my cell. Another way is to use cell notation or a cell diagram to denote what is in the cell. And this is how the cell diagrams work. So we write from left to right, just like a book. And so it's always going from anode to cathode, alphabetical, which is also helpful. And we always put the electrode first, followed by a line, because we've got a phase change between the electrode and our solution. What's in solution and its concentration, if that's important. The 2 double lines indicate a salt bridge. And then I'm over the salt bridge and into the other half cell. And in this case, I've got silver ions in solution. And then I end with the final electrode. So it's always electrode, what's in solution, double line for salt bridge, what's in solution, line, electrode. So in this case, we also have active electrodes. They're involved in the reaction. Let's look at an example where we don't have active electrodes. So in this example, we say write the diagram for a cell with a hydrogen electrode on the left and an iron 3, iron 2 electrode on the right. The 2 electrode compartments are connected by a salt bridge, and platinum is used as the conductor at each electrode. So since we have the hydrogen electrode on the left, right, so that's my oxidation step, and iron 3, iron 2 must be my reduction step, and that is on the right. So my cell diagram also goes left to right. First, we write what is the electrode. So in this case, it's a platinum. Then we write what's going on. So we've got H plus in solution and H2 gas in our hydrogen electrode. We have a line there because there's a phase difference between gas and aqueous. Our double line tells us that's where the salt bridge is. And then we've got iron 3 plus and iron 2 plus happening on the right side. So that's my reduction step. And that is going to be connected via a platinum electrode on the other side. So I think it might be helpful at this point to think about what is the reaction going on in the cell. So we should be able to either look at the picture or look at a cell diagram and write the reaction that's going on. So oxidation at the anode, right? So on this side we have oxidation, so our hydrogen gas is going to become 2H plus aqueous plus 2 electrons, right? 0 charge here, plus 1 on each hydrogen, so that's a 2 electron process. The reduction is happening at the cathode, so we are going to have to add an electron to iron 3 plus to make iron 2 plus. So, oops, it just went nuts on me. So again, I want the electrons to balance out. So I'm going to attempt to multiply that entire equation by 2 and add them up. So the overall equation, right, are electrons are going to cancel out. So we get hydrogen gas plus 2 iron 3 plus ions going to 2 H plus ions and 2 Fe plus 2 ions. That's our overall reaction. Let's do one more example to finish out this video. So in this example, we are going to write the chemical equation for the reaction corresponding to the following cell. Looks like we have another hydrogen electrode, and then cobalt with platinum again. And given that the cell potential is positive, is the cell reaction spontaneous as written? So first up, we'll think about, well, that same oxidation step. So this half looks very similar to the previous example. So we're going to have oxidation where hydrogen becomes hydrogen ions, protons, and electrons. And the reduction step in this case is cobalt 3 plus an electron going to cobalt. So again, we need to multiply by 2 so that our electrons cancel out. And we add it up, and we're going to get hydrogen plus 2 cobalt 3 ions makes hydrogen ions, 2 hydrogen ions plus 2 cobalt 2 plus ions. So since the cell potential is positive, as we saw earlier, delta G equals negative NF E. So if this number is positive, that'll give me a negative delta G, so it will be spontaneous. Okay. So for practice and for clarity, there are 2 textbook animations that I think you'll find really helpful for this. The first one I already mentioned, the zinc-copper cell animation, and the other one is just the first 6 sections of the cell potential animation. So those you can get to from your digital landing page in your textbook or from SmartWorks if you're on that page where you start SmartWorks, where you hit the SmartWorks button. Instead of hitting SmartWorks, hit text animation button. These are also links. So if you open up this PowerPoint file from Sakai, you can also just click on these and it'll bring you right to that link in your textbook. There's also another activity to practice this so that you can practice writing reactions from cell diagrams and from the reactions going back and forth to cell diagrams. And again, if you have any questions, be sure to stop in at an opportunity for questions Google Meet. Hope to see you soon. Bye.